Second one, if A comma B are any two events of a random experiment, such that P of A does not equal to 0, P of B does not equal to 0, then P of A intersection B is equal to P of A into P of B conditioned on A, or P of B into P of A conditioned on B. So now this is known as multiplication theorem on probability. This question may be asked in the examination. State and prove multiplication theorem on probability. If you are asked that question, first you write down the statement A comma B are any two events of a random experiment such that P of A does not equal to 0, P of B does not equal to 0, that will definitely they will occur. So then P of A intersection B is equal to P of A into P of B conditioned on A is equal to P of A into P of A conditioned on B. Otherwise, what is meant by B conditioned on A means after the occurrence of A, B occurs. What is meant by A conditioned on B means after the occurrence of B, A occurs. So let us prove it now. So given A comma B are two events in a random experiment. From conditional probability. From the definition of the conditional probability, P of B conditioned on A is equal to N of A intersection B by N of A. Now you do one thing, divide both numerator and denominator by n of s, sample space, number of elements in sample space. Now this can be written, so P of B conditioned on A is equal to N of A intersection B by N of S. This is N of A by N of S. Just observe numerator and denominator. Here favorable cases by total number of cases, favorable cases by total number of cases. That is the classical definition of the probability. This becomes P of A intersection B by this becomes probability of A. Cross multiplication. P of A intersection B is equal to, we get P of A into P of B conditioned on A. Similarly, we can prove P of A intersection B is equal to P of B into P of A conditioned on B. Hence, it is proved. Very simple proof. Third one, if E1, E2, E3, so on En are mutually exclusive and exhaustive events in a sample space, yes, and A is any event associated with any EI. I take the values from 1 to n, that means any EI such that P of A does not equal to 0, then P of EK conditioned on A is equal to P of EK into P of A conditioned on EK by sigma I runs from 1 to n P of EI into P of here A conditioned on EI. Do you know what is theorem? So, this theorem is known as Bayes' theorem. Bayes' theorem. Bayes' theorem. So, in the examination you may be asked to state and prove Bayes' theorem. The statement is compulsory, you have to remember. So, you have to keep in your mind. You have to just go through the same as it is, you have to remember. You have to write the statement in the examination. If the statement is not given, because I suppose that I think that the question may be given like this, state and prove Bayes' theorem. So, proof. See, E1, E2, E3 dash dash En are mutually exclusive and exhaustive events in a sample space. That means, so E1 intersection E2 intersection E3 and so on intersection En is equal to null set pi. E1 union E2 union and dash dash En is equal to yes, sample space yes. A is associated with EI. So, that means even E1 intersection A, E2 intersection A, E3 intersection A, even En intersection A also pi. So, now we have to prove that this one. So, now let us write like this, prove E1, E2, E3 dash dash En are mutually exclusive and exhaustive events. So, that means here, okay, from by multiplication theorem on probability. Let us write P of Ek conditioned on A, that is P of Ek intersection A by P of A. Say equation 1 this is. Okay. P of Ek. Now, P of A we have to find out. P of A. P of A means here since they are mutually exclusive, we have union of EI, I takes from N is equal to S sample space, and A intersection EI is equal to pi. A intersection A is equal to pi. So, now consider P of A. P of A means this is nothing but we can write P of S intersection A. You replace S value here. P of union I is equal to 1 to N EI intersection A. From union axiom, this can be written like this: sigma I is equal to 1 to N P of EI intersection A. Okay. So, now this we can write using multiplication theorem. I is equal to 1 to N, this is P of EI into P of A conditioned on EI. Okay. We can write like this. Substituting in equation 1. So, substituting in equation 1 from 1, okay, from 1 let us write P of Ek conditioned on A is equal to, this is nothing but P of Ek into P of A conditioned on Ek by P of A is replaced by this value, okay, that is nothing but sigma I is equal to 1 to N P of EI into P of A conditioned on EI, that is all. This is somewhat actually very important problem. So, be careful while doing this problem actually. So, you concentrate more on this one. First statement, after that the concepts we have to make use of.